everyone. Good day. My name's William Malik. I'm the Vice President for Infrastructure Strategies with Trend Micro. Today, our topic is how we bring the concept of zero trust into the world of industrial IoT. You might ask, why bother? The reason is that recent events have shown that conventional security approaches, as they are understood generally, fall short of what people need to have a truly trustworthy industrial Internet of Things infrastructure in place. In the course of this talk, I'm going to spend the first half talking about how we perceive the industrial IoT environment to emphasize what I mean by shortcomings. And in the second half, I will introduce the concept of zero trust, talk about where it came from, what it means, again, how it would apply specifically. The fulcrum for this is going to be mapping zero trust against IEC 62443. That's a piece of work that I have not completed at this moment. However, it is very high on my priority list. I think it's crucial to understand that. The model for industrial IoT that I'm using is actually not something we've whipped up here. I'm going to reference the special publication that NIST put out last year that talks about how those components work together. The most important message for the second half is going to be that zero trust is not a product and it is not a suite of products. It is a design goal. It's an architectural pattern. It's a way in which to arrange things. So at the end, what I'll have is a list of about 8 or 10 suggestions on how to get closer to a zero trust environment. And hopefully by the time we get to that list, it'll be entirely clear as to why one might want to do that. Just as a side note, the graphic on the screen here was not developed randomly. This is actually a visualization of a collection of data involving about 50 of Trend Micro's customers. And what we're looking at here is the better part of a year's data aggregated, and then what it depicts is the discovery of ransomware, following it through various parts of the organization, seeing where it did things like attempting to drop other malicious programs, and then, of course, the ultimate resolution. We hired about half a dozen data visualization artists. We actually found one who works within Trend, and these are the backgrounds for the presentations we've been using for the past year or so. We call it the art of cybersecurity. I apologize for the throat. It's been wonky weather here in Connecticut. So, looking forward to seeing you in your next meeting. So let us begin. First of all, the problem. These two items were taken from the June 1st edition of SANS News Bites, just to pick a day at random. What did they have to say? First of all, Government Computing News published an article referencing a memo from an officer in the U.S. Army saying that all remote workers should turn off their IoT devices that are capable of listening because they pose a security risk. I found this to be somewhat humorous. I'm not a technophile. I do not have a whole bunch of smart IoT devices. I don't have Alexa, I don't have Siri, I don't use Cortana, but I do have a smart TV. I do have a couple of cell phones. There is a Nest, which I don't think listens. But the point is that all of these things are now recognized by the Department of Defense as being a security risk. Years ago, when I was visiting NSA headquarters, and this will give you a clue as to how long ago it was, Furbies were not allowed on premises because the concern was they would start speaking confidential. So that's a humorous note about what was reported yesterday. The more serious note on what was reported in yesterday's news was the fact that last Friday, Siemens published an urgent firmware update because it turns out that 2 series of their PLCs had a high severity vulnerability, which would allow, the diagram is on the right there, which would allow code to escape the sandbox and run undetected on board the PLC. So those of you who are running Siemens PLCs of this model, the SS7 1200 and the S7 1500, should probably take a look at updating the firmware for that. Now, as a security professional, I am duty bound to tell you to patch your systems regularly. As a person who's actually lived in the real world for a time, I know that that is extremely hard to do. So what you need to do is to say, how do we go about patching something when it's really hideously bad, when it's really horrible? And if you can perform that, then you're in the top half of the class. There are environments, however, where it is impossible to patch because the systems themselves are configured to be unmodifiable. Probably the most serious example of that that was commonly known would be healthcare. In the US, medical equipment must be approved by the Food and Drug Administration. The FDA approval process can take from 5 to 7 years. Now, there has been work done recently to try to speed it up to get it down to 2 years. But what that means generally is when you are in a hospital bed in the United States, the software in that bed is probably running on an unmodified copy of the original Windows 7 OS. That may give one pause. And given that most hospitals are fairly simple in their design, they have a very flat network, which means if a bug gets in there, it will go like wildfire. And in fact, we saw something similar to this happen at TSMC 2 years ago, where a technician took their personal computer onto the floor where they were diagnosing robots, doing regular maintenance, plugged the PC into one of the industrial robots on the floor and introduced a virus, because that robot also was running an original version of Windows 7. And within 40 seconds, that virus propagated across the entire floor, which in this case means 100,000 robots were infected. The site had to be shut down for a week. The impact was felt in Taiwan's GDP. This is a level of risk that most individuals would not tolerate knowingly. The problem was the assumption that this is an isolated environment. We have a perimeter here. And as long as anybody inside the perimeter is supposed to be there and is okay, then we're fine. The notion behind zero trust is there is no perimeter. And I'm getting into the second half of the presentation. So that's just a foretaste of what it is we're thinking about and why it is we're looking at this. So the market's growing real fast. Now, this is not made to poke fun at market researchers. I worked at Gartner for 11 years, and I certainly, was involved in the creation of documents that talked about the growth rate and so on and so on. What we're seeing here are three divergent predictions of the size of the market by 2025, 2027, 2028. The different results, of course, come from different starting points, depending upon what they were measuring. The folks at Market Research Blog assessed the market in 2021 to be about 370 billion. The folks at Meticulous Research had a lower figure of 104 billion, and the folks at Grandview felt the market was about 200 billion. The point is, and this is what's bold-faced, is it's growing real fast. If your CAGR is 18%, that is, if you're growing 18% a year compounded, then you double every 4 years. And that seems to be the consensus pace at which the market is growing. I think the Grandview folks, because they started a little earlier, came from a much lower base, and so they observed a much higher growth rate, which accounts for the what we saw at the end of the last decade. It's getting really big, and it's going to get much bigger. Prices are coming down. Technology is improving. Battery life is getting longer. All the constraints that had gotten in the way of an effective IoT deployment, especially in industrial contexts, are being moved away. Progress towards 5G is going to help a lot. Two things that 5G brings, and I'm talking about real 5G, not the stuff that your phone tells you it's already ready for. The 5G that'll be available in 2026 when they finish RHEL 18 and start building equipment that conforms to that spec. That will give us sub-millisecond response time. That will give us massive densities, 1 device per square meter across a square kilometer or more, million devices in a square kilometer. Those kinds of enhancements will greatly increase the stress on the software supporting these environments. And once you've got that many things with the computers to scale up, we'll see additional interesting problems. There's one having to do with the rate at which we can bring up and tear down virtual environments that I expect will be another roll the counter type challenge, like the Y2K bug was, like the global GPS satellite bug was just over 2 years ago now. Those things are coming, and we've got to be ready. We cannot persist in the illusion that the world is safe and there are perimeters, that everybody's in their own walled garden. It just doesn't work that way. What we're seeing when we look at IoT security in industrial contexts is that, according to a study that we did last year, a trend, about 38% of organizations really got the security team, their IT security teams, involved in IoT products. Now, granted, not everybody has a huge IT security team that has folks that they can spare, but this stuff is important, and you need to have that skill to hand. Typical organizations observe 3 attacks on their connected devices over, I guess this is a period of a year when we did the survey. So that means everything is going to be hit, and that includes stuff that is allegedly inside of a secure perimeter. So the message there is we need to do a better job of detecting and blocking threats internally. We need to consider microsegmentation. That means busting the network up so it's not flat. Of course, there's a threshold there. If you do too much microsegmentation, you end up, you solve the data lateral movement problem, you solve the exfiltration problem, but now you have a blue million policies that you have to manage in order to keep track of what are all of these firewall or zero trust network barriers are working correctly. And on the other hand, 93% said that they saw that the way they'd implemented IoT left them vulnerable. So there's awareness. There's awareness, and there's data to suggest that the problem is real. But there's not enough when it gets to getting the right resources in place to solve the problem. And that leads us to the challenges we see securing industrial IoT. And for some reason, my slide, there it goes. The 4 instances that I want to speak with are, first, the complexity of the infrastructure. As we scale up, the number of components is skyrocketing. Saudi Arabia put together a very large solar farm. I believe it ended up with something like 5 million panels. Now, each panel has 16 sensors and an inverter. So you're looking at an environment which would have 80 million components to track. That is an impossibly large amount of stuff to do. The only way to manage that kind of thing is with some sort of an automation. I almost said intelligent automation, but we're not there yet. I don't want to mislead people into thinking that there's a solution that doesn't exist. But we know what the solution has to look like, and we're moving in that direction. Managing huge numbers of components and being able to filter the data that's coming through is going to be a significant challenge. And since most organizations that are doing these things are not primarily in the security business, they will look to the side for help. And where they will look for help is some sort of a managed SOC. There are companies that now will run your security operations center for you. You need to provide them the thresholds and the contact information. It varies from too much information to just the right amount of information to not enough information. And if you've done work with process hazard analysis, you know that the only 2 choices that make sense are too much information or just right. You do not want to miss an alert that could have prevented the propagation of a piece of malware across a site that big. So how do you deal with the excessive stuff? Well, you buffer it using a managed SOC. The mixed IT and OT networks, this is the right way to talk about what sometimes shows up in the news as IT-OT convergence. There is no IT-OT convergence. These are two environments, and they are in contact more and more. I mean, Modbus was created the same year the internet, the predecessor, DARPANET, first went live. They both date from 1969. I was a freshman in college. Hope that's personal information. Please delete that. The point is that they've been around and they've been borrowing from each other for a long, long time. The challenge there is that the nature of the borrowing has been things that IT seems to do well. OT says, this is proven technology and we'll take it. And as a result, we went to Windows networking and OT networks in the late 90s. We introduced OLE, Object Loading and Execution, OLE from Microsoft into IoT. And then Microsoft discovered that OLE version 1 wasn't very good. And so in Service Pack, was it 1A? They got rid of it, which meant that all the IoT devices that were using that stopped working. That is not the way you want to do that. What we're now learning is that people in IT will go forward with almost good enough, and it's almost a design philosophy. You know, if it works on the mainline paths, ship it. And that is the core of the philosophical difference between what software engineers do and what every other kind of engineer does. Because the real architectural goals of engineering in the real world are, first of all, fail safe. And second of all, even if the system collapses, have the core service remain available. If an escalator fails, it doesn't break loose and go rolling down and throw people akimbo. If an escalator fails, it comes to a stop slowly, smoothly, and locks in place. And it's still useful. It's still a stairway. Whereas in the IT environment, confidentiality, integrity, and availability, which is a somewhat contorted way of saying data shall not be lost, data shall not be altered, data shall not be, shall be available when needed. Those are the principles, and anything else, like maybe you have to restart the system, is considered a minor inconvenience. And that's where the mixing causes a problem, because you have an architectural fault line. And the problem isn't that OT doesn't understand IT. The problem is that IT isn't upfront about what its engineering shortcomings are. That there were actually a field like software engineering that we could actually, do engineering and consider things like safety and fundamental system availability. We're not there yet, not by a long shot. The third area with inadequate security controls, this is IT's observation that there are premises about the integrity of environments. And this is why Zero Trust is most important when looking at IT-based OT capabilities. And obviously design principles, well, I just covered that. You don't really want an environment where one group thinks that safety is paramount, the other one group thinks that unplugging it, restarting it will get you to where you want to go. So let me bring up our next, yes, here we are. So in the world of ICS, we found in 2020, 893 ICS vulnerabilities. Who's we and how did we find them? Trend Micro acquired Tipping Point, and with that, we became the custodians of the Zero Defect Initiative, ZDI. ZDI is the largest independent, call it crowdsourced, defect detection engine in the world. If you are an independent cybersecurity researcher and you discover a bug in a piece of paid-for software, you can try to contact the owning organization and discover on your own what their process is for appropriate reporting, or you can go to ZDI and say, look, I found this bug in this piece of code. I would like you to be able to, verify my research, ensure that it's going to contact the vendor and so on. And ZDI will take a look and say, wow, yeah, that's a live one. Here's a check for $5,000. ZDI will buy the bug and then go through a formal responsible disclosure process with the vendor, which is then given 60 days to produce a remediation. We get through ZDI about over 2/3 of all the defects from all of these type programs in the world. I mean, we're very much the leader in this. Substantial amount of information is brought to the attention. And because it's such a big organization, organizations that have defects that are reported to them by ZDI tend to take it very seriously. Fact was, in 2017, defects in OT components tended to be remediated after 270 some days. That's almost 9 months. Nowadays, they're generally pretty close to the 60-day mark. We started getting defects reported there, long ago. We weren't frankly getting much luck at getting them fixed, but the tide has certainly turned, and now a defect in an ICS component is treated just as seriously by that vendor as a defect in, Adobe or Microsoft or what have you. So that's picking up. The rate is increasing. The volume of traffic is great. So let's move forward, and we see that OT security is not managed by IT or by security teams. It's an engineering area. It's on the production floor. It's a component in an industrial process. And so, why invite strangers from another world who speak a different language to come in and help manage things? That's the cultural problem. That's the fundamental architectural disconnect. IT security people need how to talk ICS. OT organizations should be willing to broaden their constituencies to include possible input from the IT guys. And finally, when you take a look at HMIs, they're not designed for connectivity. They're very much predicated on the notion of being in a walled garden in a secure environment. So HMI devices are what IT people would just call consoles. Again, special purpose, but the core information architecture is fundamental, PC-like device. The problem is that without the connectivity, patching and restoration and failover, hot standby configurations are non-trivial. If something fails, first of all, you want to get back online, but do you want to put something that is an exact clone of that device in its place only to have it fail a few moments later? So the design of highly available environments involving HMI or OT generally is subtle and complex. Again, Zero Trust can help in those environments. What we're looking at when we see an OT environment in the large then is a world with an awful lot of connectivity, some of which is unintentional, with an awful lot of positions where there are vulnerabilities across the board. Device hacking is not that common now, thank goodness, but it turns out there are fundamental vulnerabilities in device architecture and even in the structure of the environment as well. I'm talking about things like Spectre or Meltdown. I mean, something as simple as the language used to program industrial robots. Most of the vendors that provide robots provide a proprietary language to go with them. That language allows you to, among other things, send a message across a connection to an identified device or generic name. It allows you to download information from across the net, and it allows you to set up and execute subroutines. There is no fundamental security component in that language architecturally across any of the robotic manufacturers. It's very simple. It's direct. It's like a stripped down version of Python. You put together the script, it does what you say. The problem is that these scripts get very, very large, and it becomes difficult to QA them. There are tools that some programmers use fairly well that will help them do a code analysis, that will help them do static testing, it's called, where you take a look at the code and you try to suss out the code paths and you try to determine if there are any conditions where a particular set of inputs would cause the device to malfunction, or where a particular pattern of execution would suggest, this isn't doing what robots normally do. Robots don't normally generate 50 emails per second and send them out against a table of 5 million target addresses. Your robot's been pwned, and it's now working as a spam distribution point. So the languages themselves, it turns out, are quite vulnerable. The reason we don't see third-party vendors providing tools to do static analysis against these is because they're small populations. I mean, the vendors of these robots have, maybe a few 100,000, maybe a few million across the world. That's a relatively small population of target users. If you use a robot that has 50,000 instances installed globally, and obviously not one per organization, you use many robots in an organization, let's say there are 5,000. You now are, if you're a vendor of the software that does static code analysis, you have a market ceiling of 5,000 target customers. Well, the margins on this stuff are pretty good once you've got the first one working. But if you can spend the effort and cover, say the variant of Android that's being used properly, you have possibly 100 million target customers as compared to 5,000 target customers. And so there is no market demand. However, hackers don't see things that way. They will poke around wherever they can, and once they get a tool that makes it easy, then they'll go nuts. Race, as a for instance. They stumbled across Colonial Pipeline stuff. They took it offline. It caused an international incident, and Darktrace did the right thing. They said, we didn't mean it to do that. We'll do a better job. And then a couple of days later, they said, we're going out of business. We're not going to do this anymore. The downside is just too great, which is how computer criminals say, please don't send the predator drones after us. And of course, it was all nonsense because they hit again a week later. So don't believe it when a career criminal tells you they've changed. Be skeptical. Assume they're not telling the truth. Their goal is to stay in business and to make money. It's not to placate the concerns of individuals they don't know or care about. So we get malware. Where do we get malware? We get malware from phishing emails. This is, in fact, the week of the 20th anniversary of the I love you virus. Right? You got an email that said, I love you. Oh, that's awfully nice. And the next thing you know, you've sent that same email to everybody in your contacts list. That was 20 years ago. We have gotten a little bit better. Some organizations have adopted proactive strategies to try to block that. One that I particularly like is if the email comes from an organization whose DNS record is less than 60 days old, just throw it out. If they're that new, you probably don't really need to hear from them right away. You probably can wait 2 months, and if you get an email and they're still around, then maybe it's legit and you can let it through your email system. Most bad guys who construct these servers use them for a couple of days, and then they move on to a new address. So that's an easy, quick way to get rid of certain kinds of spam. Some malware enters the system, and then we'll look around and say, "Oh, we can't attack this system. It's a comrade. It's a fellow soldier in arms." And so Brian Krebs came up with a great idea that the way to stop the Russian hackers is to install a Cyrillic keyboard on one of your devices. The malware lands and says, "Oh my gosh, Tovarish, we're not going to hit here." Brian's a smart guy. The point is that when you put these environments together, if it's a flat network, there are a lot of ways malware can get in. It can come in through phishing, but rather than throw a rock at the user community, even the best organizations still find that 4 to 5% of their employees will occasionally click on the link. The best organizations will do more. They'll segment the network. They'll block stuff from 2 new sites. And malware can come from other places. As we learned, it can come through the supply chain. Now, in the case of the issue with supply chain vulnerabilities, yeah, you can say, well, let's wait 2 weeks. Well, the bad guys will just set the timer for 3 weeks before the attack takes place. What you want to do there, again, is be involved with the communities that look for and watch that stuff. Let's begin with the assumption that you cannot build a perfect, pristine environment. What you can do is try to limit the effect. And the way to do that is to segment the environment. to take a look at network traffic to monitor for malicious or unfamiliar code patterns, indications of compromise, and then let the software block it without slowing down the devices themselves. I'll get into recommendations more, but bear this architectural model in mind as we take a look at solutions, because now we're going to move into the discussion of what zero trust is. The idea behind zero trust is to take IEC 62443 and operationalize it. And I don't have the document done which models zero trust against the standard using the definition of zero trust that comes from the NIST publication. I have the number in a couple of slides. And we're going to tell you, okay, here's what zero trust components look like when tied down to relatively speaking immutable standard. So we'll get into the details about that. So given the kinds of problems that we see in the environment, and this does not restrict itself to industrial control systems, this is IT systems generally. One of the problems is the identity of devices. We need to know which component is which. If you run an environment where you have unnamed devices, or you have devices that have the same identifier, your environment is now unmanageable. You don't know which one of the two is the one you want to modify. I did a paper at Gartner in the early 90s called Crossing the Threshold of Complexity. And the problem here is once you get past a certain number of devices, you roll a counter, and now you have either anonymous devices or devices that are synonyms with other devices. You can't manage that. The traffic on the network is a potential architectural vulnerability because the internet was not designed for security. We see instead anything and everything can go through. You can decide which port you want to aim it at, but a lot of stuff can still see the traffic as it passes by. The instability of endpoints is an architectural vulnerability. There is no standard for what a good endpoint should look like. There was a philosophy called network access control that spoke to that in very specific terms, originally in the late 90s. It hasn't been carried forward, but it's recurring in the zero trust environment now. Server integrity, this is the problem with the host devices that are on premise. How recently has the software been updated? Is it possible to update the software at all? What mechanisms are in place to deal with defects, to deal with necessary updates? There was a paper written actually at IBM in the early 1980s by Ed Norton, I believe was his name. I should have the reference in the references at the end of the deck, where he said, once you've passed a certain number of in-service hours, you should not apply preventative maintenance at all, because the software, if you will, is work hardened. And given that the defect rate for fixes is an order of magnitude worse than the defect rate for new code, introducing a piece of preventative maintenance to eliminate a defect that you've never seen has a significant chance of introducing a defect that will then cause you trouble. So you run code for a couple of years, you're not changing the environment, just back off on the preventative maintenance. Corrective maintenance, yeah, you got to fix that right away. So that works if you, in fact, do install corrective maintenance and are able to do that. The point is we haven't done that kind of study with ICS environments. The diversity is too great. That study, which was published, I believe in 1984 actually, was done within IBM, and it was looking at IBM software for mainframe environments, products that mainframers like IMS and CICS and the MVS operating system and so on. That was the code base that they were working with. But server integrity is a general problem, and what we've learned recently is that supply chain and cloud integrity is also a problem. Now, let me tip my hat to the manufacturers of cloud services. This is the middle of 2021. If we go back 2.5 years, we will find 2 instances where a cloud provider actually shipped a defect. All of the other problems you've heard about leakage of data from cloud or inappropriate disclosure or inappropriate access, all of those are the result of misconfigurations. And the sad truth is that there are an awful lot of options when you configure a cloud service. When you create a new cloud instance, it is perfectly secure. The only person who can mess with it is you, the creator. Somewhere between the time you created it and that service goes into production, someone somewhere deliberately altered a configuration that rendered that stuff vulnerable. Now, again, I'm not throwing a rock at the people or the process, although I did kind of chuckle when I heard someone say that DevOps is the Ricky Bobby of software, just go faster. The fact is that you really do need to take a look at what options you're putting in there and what they're doing. And given the volume of them, given the dozens and hundreds of options you can choose from, it's helpful to use a technology that can do a scan and tell you how close to the mark you are, and such stuff exists. So the problem is theoretically solved. That's how the mathematician in me says, there is a problem, a solution exists. Deploying it and getting it up there is crucial, especially as we see the steeply accelerating number of devices and number of applications that will be going forward. So that's the architectural rundown of the diagram we saw 2 slides ago. So now let's get into where Zero Trust is. This is a picture of the great leader Joshua, who is about to tear down the walls of Jericho. The Jericho Forum was created in 2004 to get people to be aware of the fact that there is no perimeter, there are no walls. Network access control as a philosophy showed up in the late 90s. The idea there was you don't allow somebody into the network unless they prove who they say they are, and the device passes a health check. Georgia Tech has a network on campus, and it's pretty much open. You can attempt to connect to, gatech.edu or whatever, but when you do, a couple of things are going to happen. First, you're going to have to identify yourself. You're going to have registered ahead of time with some sort of a user ID, and if you don't, you can't get in. And even if you do get in, the next thing that happens is their network access control software is going to evaluate your device, and they're going to see, do you have the right, not the right, but anti-malware software on there? Are you using something? Are the signatures relatively current? Have you run a scan? Which operating system are you using? Has it been patched recently? Are there any indications of misbehavior, like a whole bunch of inappropriate traffic coming off this device? So there are reasons why we would want to keep that device from joining the network. And if there are reasons, then what ends up happening is your system is put into an anti-room where you can take the time to apply patches, run a malware scan, etc. And then once that is done, you can say, may I please enter again? And if you're in, then you are allowed to join the thing. That's network access control. Good idea. Unfortunately, it didn't really make it to the mainstream, although such things as user behavior analytics arose from it, and that had a fairly significant impact in the first half of the last decade. The Cloud Security Alliance, which was somewhat of a successor to the Jericho Forum, looking particularly at cloud, came up with a cloud control matrix, a set of principles that are compared with ISO 27001, going standard having to do with IT system security that goes back all the way to British Standard BS 7799, which ran out in the 90s. The point is that Zero Trust takes these ideas and adds the following assumptions. I want to trust nobody. The principle of least privilege is assumed. The fact that you are on a network does not mean you belong on the network. I'm still going to request authorization before you use things. I'm going to request authentication. I'm going to validate you. I'm going to validate your device. So we're looking at the notion of identity-centric security. Everything has to have a name. The names of those things that are allowed should be pre-recorded in some sort of a ledger. And this is why I talked about the identity areas being crucial to Zero Trust. Here's the standard. NIST Special Publication 800-207 defines the Zero Trust architecture. It shows how it can be used, and it is the basis for which we will compare it. And this is my to-do, that I will develop a piece of research that compares it with IEC 62443, so we can see exactly how it applies. Not that much of a moving target. The IEC standard is undergoing revision for other purposes. I am not going to be requesting any changes to that standard. Instead, I will be tracking where it is at the moment. But this is a free publication. If you are interested, you can certainly go to NIST and get a copy of it and take a look and see what's there. So how do we get to the zero trust environment? Well, there are a lot of ways. One has to do starting with verifying the identities. And here we're saying multi-factor authentication. If you have a crucial service, if your ID is able to, say, modify firewall rules, if your ID is able to spin off processes that run on other pieces of hardware, then we want to make doubly sure you are who you say you are. Static passwords are not adequate anymore. In fact, I just read a piece that the organization Have I Been Hacked is now sharing its entire database with the FBI to help track down people who have been the victim of scams and, more importantly, the perpetrators of scams. We want to close down access to the network. We want to microsegment networks. We want to introduce DMZs where appropriate, not so many that you now change one problem of a flat network with another problem, which is too many mappings and protocols you have to keep track of. The default for applications is deny execution. That is, we're doing application whitelisting. The and more is a way to talk about things like taking the good ideas out of network access control and user behavior analysis and bring them into the 21st century with a predicate on identity so that we can have a, how good has the device been recently? How good has this device been historically? And I won't say any more about that. And the whole point of this is to get us to an environment where we can see, what's going on in the SaaS environment and move beyond VPNs. The problem with VPNs, I work from home, and I do have the ability to connect a VPN to one of our servers on the West Coast. I don't use it because all of the applications that I use have their own security patterns that I go through. I use multi-factor authentication to get to email. I use multi-factor authentication to get to the environment that houses marketing data. I do not have access to development systems at all. So we're getting beyond VPNs because if I have a VPN, then anything that happens on my machine gets a free pass to everything that happens on the back end. And that just is too coarse-grained a solution. Fine-grained, think of it as a fine-grained VPN, a VPN that exists for the duration of the transaction. I authenticate myself to a resource. I'm then able to do what I need to do within those constraints. And when I'm done, we tear down the connection. If I were to do online banking, that would be the kind of thing I'd want to do. I have no access to it. There are no cookies that keep my password there. When I click on the link, I get the same screen that everybody else does. And then I go through a logon process. I will have already been registered. And then I go through a second verification. And now I can take a look at my account. I can move my money. I can be done with it, get a record of the transaction, disconnect, and tear down that infrastructure. That's the kind of zero trust network access that is a component of this. And together, when you add that with the cloud access security broker and secure web gateway technology, that's CASB and SWG, you get a thing we call Secure Access Service Edge. Now, Secure Access Service Edge is the general name for how you authenticate yourself in a cloud environment. It's actually the name for various vendors' suites of products that include the acronym SOUP that we've just gone through. This is one of the ways to get to zero trust. Combine a cloud access security broker that says what cloud services you're allowed to get to, which ones do we not allow you to get to, what authentication we have to get in, and how do we establish a secure link to that specific application was there. That's what goes behind SASE. So why is it so hard to secure ICS? Some of the systems can't be patched. You modify the software on a hospital bed, and you've just lost your FDA certification. You can't use that bed anymore. There is no antivirus. We don't have the spare cycles on PLCs to run scans or to store patterns. It's too easy to get into environments once you're there. The networks are too flat. The environment is much more difficult to run in than we've seen traditionally. It's not the place where conventional home office type IT equipment can thrive. The conflicting architectural mandates, that's the fact that, again, IT people have lived for too long in a world where, we'll presume that whatever we're doing isn't that important, so we can turn it off and bring it back up. And, if you have to turn it off, then, why worry about smooth landings, comfortable, staged, fail down, shut down. That's not part of the mindset it needs to be. And the worldwide deployment just means it's very tough to get things around. So last few seconds, what do we want to do? We want to segment the networks where possible. We want to take a look at our safety systems, and that's a tip of the hat to Joe Weiss. We want to make sure our network traffic isn't carrying malware. Sometimes this means, in order to avoid impacting performance, you're going to have to consider out of band. You're going to have to consider a second network for some areas where you do your monitoring. We want to audit our supply chains. We want to take a look at the stuff we're getting from folks who are sending us code, as well as folks who are sending us data, as well as the folks who are sending us stuff. We want to upgrade our OT when possible. The newer generations of technology do have secure engines built into them. ARM and Intel are doing that. You now have a secure core in which you can do things like run a scan, store a pattern, generate a cryptographic signature, analyze a digital signature, create a public key. Again, it's not just enough to have it in the hardware. It's got to be provided by the vendor as well. Get a smart, eloquent, rational IT security person in on your conversations where you can. In the area of 5G, use the non-public networks. The local stuff allows you to have complete control over who can connect what, and the range is very scoped. It is more secure by design than Wi-Fi. It doesn't leak all over the place. Use secure coding practices, and this means take a look at the script you're creating when you're, say, automating robotics, remembering that there are vulnerabilities, the languages are relatively weak, and consider running that managed SOC to handle the range of incidents. Here are some of the references that I spoke with into the document, into the presentation, and just wanted to let you know this artwork was created by Brendan Dawes. Thank you very much for your time and attention. I hope to be able to see you in person.